Hello students, welcome to my YouTube channel. In this video lecture, I'm going to answer questions from sample paper number 4, RK Bali navigation book. This is the 4th edition book. If you have any other edition like the 5th or the 6th one, no problem. The questions will still remain the same in those edition books also. So let's start with question number 81. The BFO selector, the beat frequency oscillator on an ADF receiver is used to do what? Hear the ident and must always be switched on. Find the loop null position. Hear the ident of some NDB stations radiating a continuous wave signal. Okay, so BFO. BFO means beat frequency oscillator. Now the frequencies on which your NDB operates, that is starting from 190 to 1750 kilohertz. This main frequency band, this carrier waves. So on this, you cannot identify or hear the identification of NDB stations which work in this frequency band beginning from 190 to 1750 kilohertz. So in order to enable you to hear the identification of the NDB station to which you are going to tune and use that for your flight, there is another provision made called beat frequency oscillator. This beat frequency oscillator helps you to identify the NDB station, to tune to the NDB station, hear the identification, and make sure that you are tuned to the correct NDB station. Now, this beat frequency oscillator will induce an additional frequency. You have the main carrier wave, the main wave of NDB station, and in addition to this main carrier wave, there will be another audio frequency generated by this beat frequency oscillator in the receiver of your aircraft. And the normal frequency of this beat frequency or oscillator generated audio wave or audio frequency will be around somewhere around 1000 hertz, something like that. So this frequency or this audio tone that is generated by BFO helps you to hear the identification of the NDB station. So that is the job. Now there are two types of emissions, NON, A1A, NON, A2A. So NON is common to both types of emissions, where it means NON is the transmission of an unmodulated carrier wave. Unmodulated, that means the beat frequency oscillator has not produced any audio tone. The carrier wave is the only original wave, which could not be detectable on a normal receiver. Like I said, you cannot detect this normal carrier wave of NDB station, okay, just normally without using any other external help. In order to hear that or identify that, detect that, you must use an additional equipment called BFO. So BFO is provided on ADF equipment. When selected, BFO produces an offset frequency. Now what is the meaning of offset frequency? An additional frequency in addition to the original frequency. The original frequency can be anywhere between 190 to 1750 kilohertz. So this additional frequency, that is this audio tone, can be that is the addition to the original one. Now this audio tone frequency can be 1000 hertz different from the original frequency. Okay, it's just like DME. DME, the interrogation signal and the transponded signal are plus minus 63 megahertz apart. Similarly, here the beat frequency oscillator produced audio tone will be different from the original carrier wave frequency by 1000 hertz. That is called offset frequency, which when combined with the received frequency produces a tone between 400 or 1020 hertz. Now, if for the A1A part of the emission, you need to switch on the BFO for tuning, identification, and monitoring. For non-A1A part of the emission, you're going to use your BFO, switch on the BFO for tuning, identification, and monitoring. For non-A2A, you're going to use BFO only for tuning. For identification and monitoring, you did not keep your BFO on for that two purposes. But for A1A, you need your BFO on active for all three motives, that is tuning, identification, and monitoring. So, the correct answer here is Here the ident and must always be switched on. No. If the emission is known A to A, it can be turned off for identification and monitoring. So correct answer here will be option C. Here the ident of some NDB stations radiating a continuous wave signal. Next, question 82. What is the color sequence when passing over an outer, middle, and inner marker beacons? Very important. So the color sequence beginning from outer, middle, and inner marker is beginning from the outer marker BAW. That is BAW. Blue, amber, white. Okay. So for outer it's blue. For middle marker it's amber color. For inner marker it's white color. So the correct answer will be BAW. Okay, so option A will be the correct answer. Green is wrong. Okay, we do not have green color there. And Charlie is wrong. The chronology is wrong. So, next. The outer marker of an instrument landing system transmits on what frequency? Very important. Just like the colors, you must also remember the frequencies. The outer marker transmits at a frequency of 400 hertz, correction, 400 hertz, middle marker 1200, 1300 hertz, and the inner marker at 3000 hertz. So remember this table. Remember the colors blue, amber, white. Remember the modulating frequency 400, 1300, and 3000 hertz. Remember the pitch low, medium, high. Remember the ident. First, for outer marker it is dashes. For inner marker it is dots. And for middle marker it's combination of dots and dashes. Okay. Next, remember the distance. Outer marker is 6.5 to 11 kilometer. That is 3.5 to 6 nautical miles from the touchdown. Okay, not the threshold, from the touchdown. Middle marker is 3,500 feet plus minus 500 from the touchdown. And inner marker is quite close to the touchdown. That is 250 feet, say like 1,500 feet. Now the outer marker transmits on a frequency of 200 hertz and is modulated by alternate dots and dashes. 75 megahertz modulated by alternate dots and dashes. 75 megahertz modulated by Morse code 2 dashes per second. So correct answer is option C. Now all marker beacons transmit on a main carrier frequency of 75 megahertz, and this main carrier frequency is modulated by another frequency like 400 hertz frequency, 1300 hertz for middle marker, 3000 hertz for inner marker, like that. So read the question carefully. Here they have asked the transmission frequency, not the modulation frequency. And like I said, the Morse code for outer marker is 2 dashes every second per second. So that is right. Question 85. ILS glide paths provide azimuth coverage dash each side of the localizer center line to a distance of dash nautical miles from the threshold. So very important. This is your center of localizer antenna system on the opposite end of the runway. Okay. So beginning from there, you have first your localizer coverage extends to a distance of 25 nautical miles, 10-degree either side of the course. Okay, approach course. Then, if the distance is 17 nautical miles, the angular coverage is 35-degree on either side of the course. Okay, so you will select the appropriate option. Let's check the options here. Question 84. ILS glide paths provide azimuth coverage 17-degree each side of the localizer center line to a distance of, so that's each side of the localizer center line. So 10-degree on each side of the localizer center line. Degree either side, 25 nautical miles. So we do not have that kind of option 10-degree. We have 25-degree, 35-degree, 8-degree. So next possible coverage is If you are 17 nautical miles away, the coverage will be 25 degree either side, 25 degrees either side. So, right. So the correct answer here will be option A. 25 degree each side of the localizer center line up to a distance of 17 nautical miles. Up to a distance of 17 nautical miles. So either of them. So if the question has this option that 10 degree either side up to 25 miles, select that. If this is not there, then the options will have these values. 25 degree either side up to a distance of 17 miles. For a conventional DME facility beacon, saturation will occur whenever the number of simultaneous interrogations exceeds what value. So I have covered this question, this theory in my DME lectures. I have uploaded many DME lectures in which I have solved questions from Keith Williams, Oxford. Okay. So again, this question is repeated in the sample paper because it is important. Now theoretically, 126 aircraft can use a DME station simultaneously if none of them is scanning, if none of them is scanning at high rate. That means if none of them is in search mode. But on an average, we do assume that some aircraft will attempt lock on, will attempt to lock on to a DME station. That means use the services of a DME station. So at one time only 100 aircraft can use DME station simultaneously. Okay, can use simultaneously. So remember, for a conventional DME facility, select what option? Select 100 number. But remember, theoretically, 126 aircraft can use this station if they are not attempting to achieve a lock on. Next. The accuracy of a DME is what? Remember, it's given in the Oxford. Accuracy is plus minus 0.25 nautical mile plus 1.25 percentage of the DME distance shown to you, of the DME range shown to you. For example, DME indicator shows you are 100 nautical miles away. So, okay, your real distance is 100 nautical miles from the DME station, let's say on the ground. So, the indication given to you by the DME indicator on board must be accurate 100 miles, but there is some room of error allowed, and that accuracy, that room or that accuracy uh, error is plus minus 0.25 nautical miles plus 1.25 percentage of the DME range. That means plus minus 0.25 plus 1.25 percentage of 100 if 100 nautical mile is shown. That is equal to plus minus 0.25 plus 1.25. That is equal to 1.5. Okay, so 1.25 plus 0.25 is 1.5 nautical miles. Okay, so the system can show accurate 100 nautical mile or it can show 101.5 nautical mile, or 1.25 minus 0.25 is 1. Correct? It is 1 nautical mile. So in that case, minus 1 nautical mile. So it can show 99 nautical miles. So the room of error is between 99 nautical miles and 101.5. So any value between these two values is acceptable. Any value exceeding them will be unacceptable. Next, question 88. Which of the following cause air density to decrease? Air density to decrease. That means when air density decreases, what happens? Air density decreases, aircraft performance also decreases, also decreases. Now there are three factors that control air density. Do watch my density altitude video lecture, and all the questions I have solved from RK Bali related to density altitude, pressure altitude, measurement of DR elements chapter. I remember that. I have solved all the back questions from RK Bali. I have also answered all altimetry questions from Oxford Meteorology. So over there I have explained this concept many times. Now the density in your atmosphere is controlled by temperature, next humidity, and third atmospheric pressure. Atmospheric pressure. Correct? Temperature, humidity, atmospheric pressure. Now when temperature, let's consider temperature. Now when outside temperature increases, when it becomes warmer and warmer than ISA conditions, the density of air decreases. So when temperatures begin to rise, begin to increase, the density of air, that is the thickness of air, starts decreasing. The air becomes thinner and thinner. Contrary to this, when temperatures start becoming colder and colder, colder than ISA, the density of air starts increasing. That means air starts thickening. The thickness increases. So that is good actually. So hot temperatures, poor density or very thin density. Cold temperatures, good density or high density. Now pressure. You know that at ground levels, at lower altitudes, atmospheric pressure is more than atmospheric pressure at high altitudes, right? So density is affected by pressure. Now what happens is when atmospheric pressure is more, okay, more atmospheric pressure, that means more density of air. Less atmospheric pressure means less density of air. Third is humidity. Now, when density of air is maximum or is very high, when air is dry. Okay, dry means no moist, no moisture, no water, nothing. And when if the air is humid, like in Mumbai, okay, humidity decreases density of air. Okay, so humid air is bad for density. Hence, indirectly it is bad for your aircraft performance. Similarly, warm temperatures decrease density. So warm temperatures, hot temperatures are bad for your aircraft performance. Pressure. Low pressures, low density. So low atmospheric pressures are also bad for your aircraft performance. So which of the following cause air density to decrease? Read the word carefully. Density to decrease. If they ask you density altitude to decrease, so the concept changes. Okay, so density and density altitude are inversely proportional. So if warm temperatures decrease the density of air, that means they will increase density altitude. If cold temperatures increase density of air, that means indirectly it will decrease density altitude. Okay, so read the question carefully. Air density is decreases with increasing humidity, yes. Decreasing altitude. Decreasing altitude means you're coming to lower levels. When you come down to lower levels, atmospheric pressure increases, right? So you will have much more density. Increasing temperature is yes, but this is wrong. Decreasing altitude is wrong. Next, increasing humidity, okay. Increasing altitude, yes, when you go to higher altitudes, atmospheric pressure decreases. Decreasing temperature is wrong. Decreasing temperature means cold temperatures. Cold temperatures increase the density of air. Increasing humidity, okay. Increasing altitude, yes. Increasing temperature, that is also right. So correct answer is option Charlie. Question 89. Equivalent airspeed is what kind of airspeed? Is it indicated airspeed corrected for adiabatic compression? Calibrated airspeed corrected for adiabatic compression? Indicated airspeed corrected for instrument errors? So correct answer is option Bravo. So we have indicated airspeed first. Okay, the airspeed shown to you by the airspeed indicator is indicated airspeed. When this indicated airspeed is corrected for position error, pressure errors, you get calibrated airspeed. When calibrated airspeed is corrected for adiabatic compression, which is caused by very fast speeds of aircraft, 300 knots, 400 knots, you get equivalent airspeed. When equivalent airspeed is corrected for non-standard temperature, you get true airspeed. When true airspeed is corrected for winds, headwinds, tailwinds, you get ground speed. So remember this chronology. Next, 90. When a DME is used instead of marker beacons to provide range to the threshold on an ILS approach, and where the DME frequency is paired with the ILS, the DME indication should not be used at altitudes greater than 6,000 feet. So it's a factual question. It's given in the RK Bali. Read that DME chapter. Now, one more important thing, when DME is used for ILS approach purpose, so that DME station will only be used for that ILS approach. That DME station which is paired with ILS cannot be used for any other cross-country purpose or navigation purpose. So all the DME stations which are ILS paired will serve only one sole purpose, that is, give the distance or range information of aircraft from the threshold. They cannot be used for any other purpose for navigation or etc. Okay, so remember this point. So this concludes our lecture. I hope you have understood all the 10 questions I answered in this video lecture. Practice these questions again and again. Practice will make you perfect. It will increase your confidence, improve your time management also. Let me know how you have liked this video lecture in the comment box. Your questions, your doubts are most welcome. I request you all to share this video lecture with all your friends who are preparing for the exams. Subscribe if you haven't yet and hit the like button if you have liked this video lecture. All the best.